Hello, dedicated learner, and this is our second module of Lecture 1. The focus of this module is on applications. We go over the following 5 applications with the goal to demonstrate the versatility of machine learning. We begin by introducing a series of machine learning applications, as well as a number of classic machine learning problems. Data classification is one of the frequently encountered classes of problems. In this example, we want to automate the process of sorting incoming fish. Suppose a camera is placed above a conveyor belt that measures 3 characteristics of incoming fish. Our goal is to classify the fish into 2 classes, sea bass and salmon. In order to do so, we are designing a function f of 3 variables, x1, x2, and x3. These variables correspond to brightness of fish skin, length, and width of the fish. In the figure, red and blue dots represent training observations. Red dots correspond to sea bass, and blue dots correspond to salmon. As a result of training, we obtain the function f that takes measurements of an incoming fish of an unknown species and classifies it into one of the 2 classes. Usually, it is done by returning a negative value for one class and a positive value for the other. We return back to our spam filter example from the previous module. Here, although we have a more sophisticated spam filter, this filter calculates a score for an incoming email based on a number of built-in rules or tests, and adds a junk flag if the score is 5 or more. For instance, if an incoming email has an inline GIF, the test returns 1, otherwise 0. Suppose we have a large set of emails, which have been hand-labeled as spam or ham, and we know the results of all tests for each of these emails. The goal is to come up with a weight for every test such that all spam emails receive a score above 5. All ham emails get less than 5. For simplicity, suppose we have only 2 tests, test x1 and x2, and 4 training emails, one of which is spam. The goal is to come up with a weight vector, w, such that all spam emails receive a score above 5, and all ham emails get less than 5, as shown in the rightmost column. Geometrically, the goal is to separate the plane or the space into the 2 half-planes or subspaces. One subspace encapsulates ham emails, and the other one spam emails. There are a number of applicable models here, including the nonlinear models. We choose a simple linear model. The model f has 2 parameters, w1 and w2, that form a vector of unknown parameters w. The training consists in finding such w that the number of mistakes is minimal, ideally perfectly separating ham and spam emails. Although, as we discuss later, sometimes we purposely allow for a small number of mistakes. As a result of training, we have the following vector of weights. And the model is then given by this expression. To classify whether an incoming email is spam or not, 2 tests x1 and x2 are executed, and the results are substituted to the model f. If f is greater than the threshold, 5 in our case, the incoming email is labeled as spam. We don't really care that much about the performance on training data. We already know which of those emails are spam. It is important to keep in mind that good performance on training data is only a means to an end, not a goal in itself. What we care about is whether future emails are going to be classified correctly. Trying too hard at achieving good performance on training data can easily lead to a fascinating but potentially damaging phenomenon called overfitting. The goal is to generalize, not to overfit or memorize. To summarize, there are 2 steps in classification or label prediction. The first step consists in learning the model's parameters. This step is usually performed while solving an optimization problem, i.e. finding such parameters that minimize error criterion that is evaluated on the training set. The second step is applying the model to unlabeled data. Often, there is also a pre-processing step when data is cleaned up and features are extracted. These features are then used as an input to a machine learning system. Another interesting class of machine learning problems is regression analysis. Here we focus on polynomial curve fitting, a particular case of regression problems. We are given a training set comprising n observations of x together with corresponding observations of y. Note that y is no longer a label, but rather a value that certain system produces, and that we wish to model. In general, x is a vector. Here we choose x to be a scalar, as shown in the figure, and y is a sign plus some measurement noise. So our goal is to predict the value of y, which is our target variable, for some new value x of the input variable. So we want to fit the data using a polynomial function, our model, of the following form, where m is the degree of the polynomial and x superscript j denotes x raised to the power of j. The polynomial coefficients w0 to wm are denoted by the vector w. Having obtained the polynomial model, we are able to predict what y should be for a given x. The values of the coefficients w are determined by fitting the polynomial to the training data by minimizing an error function, e of w. The error function measures the misfit between the model for any given weights and the training data points. We can solve the curve fitting problem by choosing w such that e of w is minimized, so that the minimization of the error function has a unique solution denoted by w star. The resultant polynomial is given by the function f of x with weights w star. Besides learning the model weights, it is important to choose the right degree of the polynomial, since the degree defines a number of model parameters. For a lower degree, there'll be just not enough expressive power to adequately represent the data. Such phenomenon is called underfitting, which refers to a model that can neither model the training data nor generalize to new data. As you can see in this picture, we're trying to model a sign with a line. Obviously, there is just not enough expressive power in a line to represent a sine function. By increasing the degree m, the model becomes more flexible. In fact, for m being equal to 9, the polynomial passes exactly through all 9 data points, with the error function effectively being 0. However, as it can be seen from the figure, the fitted curve oscillates wildly and gives a very poor representation of the true function sine of 2 pi x. This is an example of overfitting, a crucial aspect of many machine learning algorithms that should be avoided. Overfitting is the antonym of generalization. We evaluate the error function e of w star on the training data. As we've seen previously, this error is not always the best measure of quality of learning. Here's where a validation set comes into play. To judge about the quality of learning, we evaluate e of w star on the validation dataset. It is sometimes more convenient to use the root mean square error, given by the following expression. The division by n allows us to compare different sizes of datasets on an equal footing, and the square root ensures that the error function is measured on the same scale and in the same units as a target variable. Taking a look at the figure, it is easy to see that the error on the validation set begins to increase at m equal to 4, so we conclude that the best degree for the given data is m equal to 3. In our next example, we are going back to classification. We are focusing on text classification. This task is also known as sentiment analysis. Suppose, given a sentence as, "I love this fun film." The goal is to train a model that classifies the sentence as either positive or negative class. In this example, to classify a sentence in one of these two classes, we construct two probabilistic models, on the contrary to previous examples. The training set consists of labeled text with negative and positive sentiment. By counting the number of times each word occurred in text with negative sentiment and with positive sentiment, we estimate the conditional probability of word occurrence, given the sentiment class. We read this formula as probability of word occurrence given the text is of class C. Now, having the conditional probabilities, it is easy to calculate the probability of the sentence S being in class C by multiplying out the conditional word probabilities. The probability of sentence S given the class is positive is greater than probability of S given the class is negative. In fact, we are interested in conditional probability P of C given S, probability of class C given sentence S. To obtain this probability, we should apply Bayes' theorem. In this series of lectures, we will limit ourselves to non-probabilistic machine learning, so we stop here. The last example in this module is about recommendation. A recommender could be considered as a push system that provides a user with a personalized exploration of a wide catalog of possible choices. Consider the following matrix that represents movie ratings by 6 different people on scale 0 to 3. We see that Frank enjoyed the movie titled Cold War, while Alice disliked this movie. The question is there any structure in this matrix? Looking at the matrix, it's hard to see any particular structure. However, factoring the matrix into a product of 3 matrices, it is easy to notice that the first and the third matrices on the right hand side are now Boolean, and the middle one is diagonal. These matrices have a very natural interpretation in terms of genres. Here, genres are our latent factors that are not explicitly given. In other applications, it might be hard to have a clear interpretations of latent factors, although they still often carry important structural information. The first matrix connects users and genres. We call this matrix users preference matrix. The third matrix associates movies with genres. Some movies have a few genres assigned to them. Finally, the middle matrix represents importance of every latent factor, genres in our example. Methods for discovering hidden variables or latent factors, such as genres, are especially useful when the number of values of the hidden variables, here number of genres, is much smaller than the dimensions of the original matrix. In next module, we will come back to this in the context of dimensionality reduction. In practice, the goal of recommender system is to provide a most relevant recommendations by predicting missing elements in the rating matrix. Here, a question mark represents the movie that the user hasn't watched yet. In this introductory lecture, our goal was to show motivational applications of machine learning algorithms. Also, I hope this module revealed the necessity of having a strong mathematical background. In fact, machine learning is based on 3 pillars of undergraduate mathematics, which are matrix theory, calculus, and probability theory. In this lecture series, we primarily focus on the first 2, and leave probability theory and probabilistic machine learning for another course. Here are a few exercises that I encourage you to tackle by yourself. Good luck!